more theorem to tackle before we become the undisputed lords of analysis. And that will be the theorem L13.5, the necessary condition of uniform convergence of a series. Theorem. Very well. Let the series n ranging through 1 to infinity of un of x be a series of functions, or a function series. Defined on some interval j if the series n ranging through 1 to infinity of un of x converges uniformly on j, doesn't matter to what, then the function sequence un, where n is ranging through 1 to infinity, converges uniformly to 0. I would like to state that this is, I would like to remark that this is in fact a perfect analogy to the necessary condition of convergence of a series, not uniform, just regular convergence, where we require that it's a necessary condition that the function which makes up later the partial sums of the series converges to 0 with increasing n, with the index increasing. This is a perfect analogy of that. So it makes sense that something like this would hold. How do we prove this? Well, the proof is very simple, just 2 or 3 lines. We know that the series where n ranges through 1 to infinity of un converges uniformly, and this means, and thus, for Sn being the partial sum of where k ranges through 1 to n of uk at x, Sn is a function of variable x as well. We have Sn converging uniformly on J. This is by definition of uniformly convergent series. Alright. Well, by the Bolzano-Cauchy criterion for uniform convergence, we have that for all epsilon greater than 0, there exists some n0 for all n greater, or for all nm greater or equal to n0, and for all x in J, we have then that Sn, Sn of x minus Sm of x is smaller than epsilon. Oh, fine. But n and m may be chosen arbitrarily. Well, then, in particular, for n, for m being equal to n plus 1, we have the same statement, that is, for our epsilon greater than 0, there exists some n0 for all n only, greater than n0 for all x in J, we have that S, the order doesn't matter, we can swap it. Sn plus 1 of x minus Sn of x. But this is, of course, nothing more than the last addend in the partial sum, because we remove all of them up to the nth one. So only the n plus first one remains. So this is actually equal to u n plus 1 of x minus 0. And this is precisely the definition of a uniform convergence to 0 of a function, say, of a function sequence, say un. And thus we have that un converge, it doesn't matter if there's n or n plus 1, un converge to uniformly to 0, which is precisely what we wanted. And this one was a quickie.